Hi everybody, welcome back to the introduction to Sora. In this episode 2, we're going to discuss the encoding portion of Sora video generation model. In episode 1, we introduced the video generation problem and compared the main approaches, VAE, GAN, and diffusion models. This is the comparison slide from the previous episode 1. The approaches have a few things in common. They all use the same encoder-decoder bottleneck CNN introduced by VAE. However, GAN added a separate discriminator module, while the diffusion model, the most popular among the three approaches, added the more complex multi-step denoising process. Both GAN and diffusion models create higher fidelity images, but the diffusion model generates more diverse outputs. However, GAN comes at a price of training difficulties, while diffusion models are slower in training and inference, as well as needing more data. This because the vision model has a more sophisticated generative process compared to the others. In addition, we also introduced Sora, probably the most sophisticated and advanced diffusion model. In this episode 2, we detailed the encoding stage, while in episode 3 we described the denoising process, and episode 4 the training procedure. Again, note that displayed Sora diagram is deduced using the official technical report and is our most likely estimate of its inner working. Sora encoding comprises of a mild compression and a tokenization step. The mild compression step is usually a small-sized VAE. This module compresses each individual image separately. The example in the figure is a 2:1 ratio image of 512 by 256 by 3 channels, reduced to 64 times 32 times 4 channels for a 1/8 compression for each dimension. This ratio can be increased to say a quarter, but practically not lowered without having non-negligible loss of quality. Tokenization is a process of converting frames into a set of tokens. Tokens are substantial but reasonably isolated unit features. Sora utilizes two techniques in its implementation. The first one is Native Resolution Vision Transformer, or NAVIT, to accommodate any frame size or aspect ratio. Second is Spatiotemporal Vision Transformer, or VIVID, to create token encapsulation that goes across both space and time. Before we describe these two, we are going to take a quick detour and discuss the transformer, as well as the vision transformer architecture. Particularly, we are focusing on our understanding of the unit token, its size and scope, and how it affects the rest of the video generation model. The transformer model, introduced by Vaswan in 2018, originally is a language model. That is, it is meant to generate strings of words to create sentence or a passage. This is very much like building a video one image at a time. Aside from generation, BERT, a specific transformer model, was able to perform various natural language understanding discriminative tasks much better than the previous models. The transformer model is comprised of the encoder and decoder portion. That is, the encoder encodes the input by creating a representation, while the decoder produces strain output. For Sora encoding, we are going to focus only on the encoder part. Here, we describe the generic transformer model, emphasizing why a transformer model is so effective, and in turn shedding light onto the reasons behind the breakthrough demonstrated by Sora. In this Sora encoding, we discuss tokenization and self-attention. In episode 3, we discussed the architecture, and episode 4, the data and learning. First, let's spell out the input words for clarity. Let's start from the bottom. We split the words into tokens. The average number of tokens in a word is 1.3. We can say that approximately 1 in 3 words have multiple tokens. We have an example here where the word can't is split into tokens can and apostrophe t. We then use a lookup table to convert each token made up of alphabets to feature embedding. This is a token level lookup table. That is, each token has one entry in the table. Note that there are about 30,000 tokens in the English language. Word2vec is a popular example. The embedding endows the tokens with some level of semantic meaning, as similarity in letters does not mean similarity in meaning. For example, the words hat and cat. We then add positional signal to encode the relative position of each token in the input. The resulting embedding can then be fed to the transformer model. Transformer model, which is a series of n transformer encoder modules, aim to add contextual information so that each token is aware of its surrounding. The contextualized token are the output embeddings, ready to be fed to the diffusion or denoising process. In a transformer module, multi-head attention is the computation that is responsible for adding contextualization. We'll now give an intuition of how this is done. First, however, please ignore the three-prong symbol referring to the KQV formulation. This is taken from the retrieval literature. We will now focus more on connecting pairs of tokens. In essence, self-attention module directly connects each token with every other token to receive information about them. Thus, the meaning of contextualization is the awareness of the surrounding tokens. Contextualization is important and powerful, especially when the meaning of a token is affected. Here is an example. The word bank on the phrase the riverbank and Bank of America have different meanings. Self-attention carries an order n-square quadratic complexity, which is why limiting the number of tokens per input is important. The diagrams show all connection of a contextualized token output. Each pair incorporates information via the KQV formulation. In addition, it also shows the splitting of the feed-forward layer so that we can know that the values of other tokens are not used in the feed-forward computation. The normalization layers, however, do need values from other tokens. We can now focus on the key query value or KQV formula. It is a pairwise computation between two tokens, token 1 and token 2. Here, token 2 is a query that tries to access information or values in token 1 through the token 1 keys. For encoding representation, token 2 is just another token in the input. Later on, for condition generation, token 2 is an encoded condition. This is cross-attention or cross-modal attention. The multi-head part is just splitting of features in the token vector. Each separate head computes KQV before concatenating the results. Transformer is an improvement over recurrent neural network or RNN, which is previously the state-of-the-art for various natural language understanding, as well as multi-frame computer vision tasks such as action recognition videos. The figure on the left shows an unrolling of the RNN, which processes one word at a time. This becomes problematic as the last few tokens dominates the context seen by the current token. If we map the RNN to transformer attention, it would look like this. The weak connections to earlier tokens are illustrated by lighter colored lines. In addition, the transformer is also an improvement over convolutional neural network or CNN, which is used in computer vision tasks. There are two reasons for this. One is CNN operates on pixel units, not regions, which is what Vision Transformer introduces. Vision Transformer, which is published in ICLR 2020, operates on image patch representation. They are computed by rearranging values in the patch into vector. In Sora's case, that would be the mild encoder compressed values. This is how it looks like when applied to the generic transformer diagram. Here, a region in an image is semantically equivalent to a word. It is not one token per pixel. It makes sense as we can easily picture an object occupying a region. Also, the more manageable number of tokens allows for Transformer to perform self-attention efficiently. One small detail to add is that Vision Transformer adds a slot for class output. This is usually for classification, where the separate output allows for contribution across all patches being equally considered. We do not add this slot to our transformer diagram for clarity. However, the addition will not interfere to the encoding process. The second reason why transformer is an improvement over CNN is that studies show in CNN the strong connections are primarily formed with neighboring pixels only. This is despite the fact that the kernel grows in scope in subsequent CNN layers. As such, CNN over-index on texture recognition rather than shape of the object. If we map CNN primary connection to the transformer attention at the pixel level, it would generally look like this. In a sense, Vision Transformer encodes texture recognition within the tokens while recognizing shape with self-attention. Now that we have a deeper understanding of the transformer model, we can construct a proper Sora token using Navid and then Vivid. Presented in 2023 NeurIPS, Navid introduced two clever ideas. One is not resizing input images to a single canonical size. It does so by dividing images of any size onto appropriate number of patch tokens, such that there is a common token size for equal scope across all images. This example illustrates the point with three different image sizes. Second idea is because the different inputs produce varying number of tokens per image, Navid efficiently packs as many frames as allowed in one run. This necessitates appropriate limitation on attention to just within individual images. The picture shows the attention limits when three images are processed in one run. Sora experiments show that there is information gain in keeping the shape of the image. One is preservation of subject aspect ratio. Another is framing or compositional information being preserved. The results show subjects being better centered in the videos. Comparison is shown in the bottom row, where the left image is trained on resized image, while the right one is in native aspect ratio. Now, the Vivid Vision Video Transformer model creates spatiotemporal encoding that accounts for region token relationship within an image and the same position within different frames. There are two ways to doing this. One is image level token that forces self-attention to forge relationship between pertinent tokens both in space and time. Another is spatiotemporal tubelet where the scope of each token already encompasses information across space and time. The paper shows that spatiotemporal tubelet is better because it integrates spatial and temporal information early on at the token level. The paper also states that they tried consecutive window frames of 2, 4, and 8, with 2 being the empirical best. In addition to token format selection, Vivid also designs new self-attention mechanism to take advantage of these spatiotemporal tokens. There are 4 options, as illustrated by the figure in the paper. We will adapt them to the generic transformer diagram for clarity. The first option is spatiotemporal attention, where every token in space and time are directly connected. It arguably performs the best on action recognition, but it is the costliest. This because the sheer number of attention connection needed over space and time. It should be noted that like many other more recent model, the normalization step in Vivid Transformer module is actually performed prior to self-attention. The diagram should then be modified to this. Here, the pre-normalization provides benefit in better control of gradient flow and it's easier to train. Second option is factorized encoder where it first performs spatial attention before temporal attention. This option provides the best of both worlds, near best performance with nearly most efficient on action recognition. This is the adaptation of factorized encoder onto the generic diagram. Note that from experiment it seems that the order of attention does not matter. The third option is factorized self-attention, where within the module we have separate spatial then temporal self-attention layer. This is how it looks like in the transformer diagram. The module has 2 additional layers within. The performance of this option, however, is not very notable, both in efficiency and accuracy for action recognition. The fourth and last option is factorized dot product attention. Here, half the heads are for spatial attention, while the other half is temporal. This is the generic diagram. Thus, the author selects the second option, factorized encoder, as the best attention scheme. Altogether, Sora first mildly compressed the input by either a quarter or 1/8 on each dimension. He then patchified the images into regions while respecting native aspect ratio. It then creates spatiotemporal tubelet tokens and uses factorized encoder attention to output contextualized token ready for the diffusion model denoising process. This process will be described in the coming episode 3. Thank you for your time.